Okay, I will continue on the lecture. It's not working. So it's chapter 3, and the sub-chapters that I will cover is from chapter 3.1 to 3.3. And in chapter 3.1, I will cover these two chapters. So, objects and properties. It's the materials I will cover is more like specific version of professors. So just keep that in mind. So there are objects, and objects have properties like topological, geometrical, something like that properties, and that properties are represented as pair of attributes and values. I will explain it as a figure later. And as objects can interact, attributes can interact also, and attributes can have hierarchy. So suppose there is a knife here, and as I told you, property is represented as attribute and value. If attribute is sharpness, it can the value can be very sharp, and if it's weight and it's 1 kilogram, something like that. So it's attribute and value as a property. Okay. And attributes, there are physical and functional attributes. Functions are unusual attributes, unlike some physical obvious attributes. And functional attributes cannot be measured by physical inspection alone. So it must be considered in a temporal context. There should be context if you consider the functional attribute. And if you see the bottom, function, behavior, and structure, these are things that can be designed and can be attribute, physical or functional attribute. So the examples of physical attributes are such as sharpness, hardness, and weight. And functional attributes of a knife can be cut, something like that. Object and properties as frames. It's an information structure and a framework by which information about an entity can be grouped together. And frame consists of slot and value. I will explain it later. So you can represent the information structure as a frame. There is a slot, offset, and value. You will see this type of table in the later part. And classes and instances. In the board, you can see classes and hierarchies. And a class is a collection of entities, where an entity is itself an instance or a class. And whereas an instance is an entity that belongs to the real world. So I have a Kia K5. It's an instance. It can be instance. And a car can be a class. It's very simple. So there are 3 ways of describing designs using the class and instances. Class, subclass, and there can be some instances. It's a hierarchy. And you can design as a class, something as a class. For example, prototype or generic design. And you can design as a particular instance of a class. you take some real world example, and then you just modify it or change it a little bit. It's a class hierarchy like this. So in the left side is class and the right side is instance. Kia K5, if we say Kia K5 instance in the real world, then it's a kind of Kia cars, and Ford Explorer is a kind of Ford cars. So the hierarchy of the classes can be represented as a tree structure or diagram structure like that. And also one class can be a subclass of two different superclasses. For example, a knife can be a weapon and a knife can be a tool at the same time. So a knife will have the attribute from both weapons and tools. And the similar example would be like this: avocado and eki. I don't know, eki and tomato. These are things that are fruit and vegetable at the same time. So, yeah, this is called multiple inheritance. So, yes, inheritance is transfer of property between class and instance. So, if you have this kind of class hierarchy, if you take this class, and this class will have the attribute of the superclass, all the superclass of this class. So, for example, it has property A, B, C, then it will have A, B, C. Okay. It's the same picture. It represents some class structure, class instance structure. And also in the upper part, you can, fire engines can belong to red object, but you can represent fire engines as a subclass of some type of superclass, and you can add the red thing as a property. So it means you can represent data structure in your own taste. You can make it an entity or you can make it an attribute like this. This is the same structure but with properties. So house have two properties and single story dwelling 1 and my house 2. So if I have a subclass under my house here, then it will be inherited 5 attributes from the older superclasses. So classes and instances as fact, it's a mathematical logic that can help to process as a programming. So there are two types of these things: a kind of and is a. These are used for representing this structure. So I will explain it as a figure. So frame thing. In the previous slide, I just showed you frame, what the frame was, and house is frame, and AKO here. AKO is a kind of house is a kind of building, right? So and the number of floors, these are kind of properties. These should be a value, integer value, constrained from 1 to 3, but we'll set default as a 1. And the usage is for living. So this is kind of frame structure. And this is the same class hierarchy. AKO here, a kind of. So beam is a super class, and simple supported beam is a subclass at the bottom. So to represent superclass and subclass hierarchy, AKO you can say like this. Simply supported beam is a kind of statically determinate beam. So you can read like this in this structure. So this is the same thing. So beam 1, let's say beam 1 is an instance in the real world, and then beam 1 is a cantilever beam, and cantilever beam is a kind of statically determinate beam. It's hard to pronounce. And statically determinate beam is a kind of beam. So you can read like this, and those tables are frame structures. So I explained about classes and attributes and properties, something like that. But there is a limitation. There are limitations because it's the real world and universe. So not everything can be divisible into discrete things. This limitation is the same as the limitation of object-oriented programming. If you have a chance to have program C++, something like that, you are familiar with this OOP, but it contains some classes and structure like that. So it's the same problem. Because the real world is not all discrete but fuzzy. So to be able to represent the fuzzy real world, you will need these type of approaches: reductionism and holism and convergence fusion of classes and things and attributes. So brief summary of chapter 3.1.4 to 5 is like this. So in the 3.1.4 I explained about object and property. And in the later part, I explained about classes and instances and their hierarchy, and inheritance between classes and the mathematical representation of the hierarchy, a kind of and is a. And sometimes the universe is not divisible into discrete things, so because it's fuzzy, so we will need these approaches. So I finished my first part of the lecture, and I'll go into the second part. It's 3.2 to 3.3. Any questions, please just let me know. 3.2 is about representing form and spatial relationships. And it's about representing and reasoning about geometry and topology. Topology, I will explain it later. Topology in terms of object and relations. And spatial form in terms of instances, classes. Okay, move on. So topology. Topology in mathematics, topology is concerned with the property of space, of its continuous deformation. If you think of, you can see that right upper figure, which is animation. A cup with a handle can be transformed into a donut. Then, let's say that's a clay. Then we say these two have the same topology. And similar with this example, in the right lower side, this cup and this sphere have the same topology. And we also, topology is also concerned with the relationship between nodes, especially in the network topology also. It's about relationship. So geometry and topology, I take some example. Take an example of KAIST campus. As a geometry, we can represent it as a latitude and longitude. But as a topology, we can represent it as an address. With this geometry and this topology will point the same KAIST campus. This figure represents the same topology and same geometry. If you see, you can see here is a line, but there is no line. So different topology, but same geometry. But here there is a line, and it can be transformed to this. So these two are same topology. Morphing is a special effect from one image to another. George W. Bush to Arnold Schwarzenegger, and Carl to Tiger. It's a special effect which can be used in the advertisement. And level of abstraction. Professor already mentioned about this. From general to specific and vice versa. Design descriptions at various level of abstraction. If you go specific to general, it's generalization. And you can just, okay. This redundancy of representation is common in a design like morphing. So if you see the morphing, there are similarities between two adjacent figures. So, okay. So for one purpose, relationship may be important. For the other purpose, geometry may be important. It's the same figure. In a circuit design, you start from the formal specification to the layout. So from general to specific, but it can be distinguishable, but it's not discrete. It's continuous, like morphing. And in the upper part, relationship is more important. I will have this and this and this and this and mixed together, something like that. And in the lower part, you will it's the detail geometry is important. So I will have something from Apple, something from Samsung, something like that. And similar with level of abstraction, level of detail is the similar thing. And speaking of level of detail, I am doing the research of reducing the level of detail of 3D CAD model as my PhD thesis. So the lower part is my research, from my research. So to reduce the detail of a 3D object or vice versa, you will require some specific detailed 3D model at a specific design. Okay, final chapter representing design intention. So design description resides explicitly in the database of a CAD system recently, and many other geometrical properties of design can be derived from them, from descriptions. So it's a kind of abduction process from the geometrical performance, like properties like performance. You just bring up come up with some new design. Is kind of abduction process. And design is a process of incrementally reducing goals to sub-goals. We call it goal decomposition. And sometimes sub-goals frequently interact each other because it's a real world. And goals are interpretations of designs that do not yet exist. So you need to have an intended interpretation. Chicken comes first or egg comes first. You just put some more value. And there is a configuration design, which is which has a fixed. If you have a fixed set of predefined components as you design it, it can be called, and the component that can be connected in a predefined ways, then you can call it a configuration design. In the configuration design, you may be easier to decompose your goals and set goals. So this is an example of goals and sub-goals. If you want it to be portable, it should be light and compact and has a handle. If it has to be compact, it should have a simple profile and no sharp projection. And if it has a simple profile, it should be cube, either a cube, pyramid, or sphere, like this. You can decompose it and select it. And it's kind of configuration design. You need these 4-5 parts to make this face, I think. I don't know. So you can synthesize from the part to the assembly. So you will have a goal to make this. And to achieve that goal, you can decompose it. And it can be making a single part in an assembly. So making those things and put together, you will have the final one. Yeah, one design is better than another by comparing their performance, it's obvious. If it's less expensive and easier to maintain, you can call it better design. And it is called sometimes evaluations. From the evaluations, you can call it it's better and it's better, or the other thing is better. And it is not always possible to produce a design that exhibits intended performance characteristics. Sometimes it can exceed or sometimes it lacks. And goals are changing. It's a nature of goals. If you think of some term project also, you set the initial goals, but goals are changing. So goals are changing. And goal is also product of the design process, not only just output of the design. And goals constitute descriptions of design that are incomplete and unresolved. So this is the final slide. So I prepared a brief summary. In the chapter 3.2, I explained about topology as well as geometry and design description at various level of abstraction or level of detail. In some design phase, relationship comes first. In the detailed design, geometry comes first. Maybe not. And in chapter 3.3, I explained about design intentions, especially about goals, and there is a goal decomposition. Goal hierarchies can be you can achieve this by decomposition and goal changes, and goal is also output of a design process, but it can be incomplete and unresolved. So this is the end of my presentation. Thank you for your attention. So if you have any question, please let me know. If not, I will finish it.